Megawatts on your mind from Lighthief. We build it, we run it, we know what works, real projects, real returns. The renewable energy podcast that doesn't waste your time. Let's go.
Hello, and welcome back to Megawatts on Your Mind. This is Lighthief, and if you've made it to episode 3, you're either genuinely interested in how solar farms work, or you've developed an unexpected fondness for listening to someone talk about renewable energy infrastructure. Either way, I appreciate your commitment. In the first episode, we discussed the state of renewables across Europe. In the second, we explored what O&M actually means for solar farms and why it matters financially. Today, we're going to get properly technical. We're going to walk through a solar farm from the perspective of someone who actually has to maintain it. Because here's the thing, when most people look at a solar farm, they see rows of shiny blue panels sitting in a field. Perhaps they notice the inverters, maybe the substation if it's visible. But a solar farm is considerably more complex than it appears. There are layers of systems, multiple voltage levels, dozens of component types, kilometers of cabling, and an entire support infrastructure that most people never think about. And if you're responsible for maintaining one of these installations, you need to understand all of it. Not just understand it theoretically, but understand it practically. Where things are located, how they connect, what can go wrong, how to access them, what to check, what matters and what doesn't. So today we're going to walk through a typical ground-mounted solar farm from the grid connection point all the way to the perimeter fence. We'll look at every major component and system, discuss what they do, how they're configured, and most importantly from an O&M perspective, what goes wrong and why you should care. Think of this as a technical anatomy lesson. We're dissecting a solar farm, but instead of a biology textbook, we're using the accumulated wisdom of people who've built and maintained these things across Europe. We've made mistakes, fixed other people's mistakes, and learned what actually matters when you're standing in a field in Poland in February, trying to work out why inverter 7 has stopped working. This won't be a complete engineering course. Those take years, not 50 minutes. But it will give you a practical understanding of how solar farms are actually constructed and what that means for ongoing operations. Shall we begin? Let's start where the electricity ends up, the grid connection, and work our way backward through the system to the panels themselves. Every solar farm exists for one purpose, to feed electricity into the grid. Everything else is just the means to that end. So let's start at the point where your solar farm connects to the utility network, the grid connection point, or point of common coupling as it's sometimes called in technical documents. The grid connection is typically at medium voltage, anywhere from 10 to 30 kilovolts, depending on the country and the size of your installation. In Poland, it's usually 15 kilovolts or 20 kilovolts. In Spain, often 20 kilovolts or 30 kilovolts. Italy varies. The specific voltage matters less than understanding that this is the interface between your asset and infrastructure you don't control. At this connection point, there's metering equipment. This is what measures how much electricity you've exported, and in bidirectional systems, how much you've imported. This metering determines your revenue, so it's rather important. The meters are typically owned and maintained by the grid operator, not by you, which means you have limited control over them. But you need to ensure they're working correctly because billing disputes are tedious and expensive. There's also protection equipment at the connection point, circuit breakers, relays, sometimes a recloser. This equipment protects both your installation and the grid from faults. If something goes catastrophically wrong in your solar farm, a short circuit, ground fault, overcurrent, this protection equipment disconnects you from the grid before you can damage utility infrastructure or electrocute someone. From an O&M perspective, the grid connection point is critical but mostly hands-off. You're not usually permitted to modify it without grid operator approval. You can't just decide to upgrade your connection or change protection settings. But you do need to monitor it, understand it, and coordinate with the grid operator when issues arise. Grid connection issues are surprisingly common. Not dramatic failures usually, but subtle problems. Communication failures between your SCADA system and the grid operator's systems. Protection relays tripping unnecessarily due to voltage fluctuations. Metering discrepancies. These problems don't always cause complete shutdowns, but they can cause curtailment. The grid operator limiting how much power you can export. Curtailment is a growing issue in areas with high renewable penetration. When there's more generation than the local grid can handle, the grid operator tells you to reduce output. You're producing electricity but not allowed to export it. It's frustrating and economically painful, but it's reality in many markets now. Monitoring curtailment and understanding why it's happening is important for asset management. Then there's the question of grid code compliance. Each country, sometimes each region, has specific technical requirements for how your solar farm must behave when connected to the grid. Voltage ride-through capability, frequency response, reactive power control, ramp rate limits. These requirements are implemented in your inverters and control systems, but they need to be maintained and occasionally updated as grid codes change. We've seen situations where a solar farm was compliant when built, but then grid code requirements changed, requiring software updates or even hardware modifications. If you don't stay compliant, the grid operator can disconnect you. So part of O&M is tracking regulatory changes and ensuring your installation remains compliant. The physical infrastructure at the connection point also needs attention. Cable terminations, insulators, earthing systems. These are typically medium voltage components, which means they're potentially dangerous and require qualified personnel. Annual inspections are standard, with testing for insulation resistance, earth continuity, and protection device functionality. Access to the connection point varies. Sometimes it's within your site, sometimes it's at the edge of the property, occasionally it's actually on utility property nearby. Understanding who's responsible for what is important. We've dealt with faults where the problem was technically in utility infrastructure, but was affecting our farm's performance, requiring careful coordination to resolve. The key point about grid connection: it's the interface between your controlled asset and the external network. Problems here can shut down your entire farm. Monitoring, maintenance, and good relationships with your grid operator are essential. Right? Moving into your solar farm from the grid connection, the next major component is usually the substation. This is where voltage transformation happens, taking the low voltage AC from your inverters and stepping it up to medium voltage for grid export. The heart of the substation is the transformer. For a typical multi-megawatt solar farm, you're looking at a transformer rated anywhere from 1 to 5 MVA, megavolt amperes, possibly larger for big installations. This is a substantial piece of equipment. It's filled with oil, weighs several tons, and costs anywhere from 50,000 to 200,000 euros depending on rating and specifications. Transformers are remarkably reliable technology. They have no moving parts, they're well understood engineering, and if properly maintained, they can last 30 to 40 years. But they do require maintenance, and they can fail, usually expensively. The transformer takes low voltage AC, typically 400 volts or 800 volts from your inverter array, and steps it up to medium voltage. This voltage transformation is necessary because transmitting power at low voltage over distance causes high resistive losses. By increasing voltage, you decrease current for the same power, which reduces losses. Basic physics, but economically important. Inside the transformer, there's insulating oil. This oil serves two purposes: electrical insulation and cooling. The oil needs to remain clean, dry, and chemically stable. Contaminated oil reduces insulation effectiveness and can lead to internal faults. Water ingress into the oil is particularly problematic. Water reduces dielectric strength. Transformer maintenance includes periodic oil testing. You extract a sample, send it to a laboratory, and they test for moisture content, dissolved gas analysis, dielectric strength, and chemical degradation. The dissolved gas analysis is particularly useful. Different fault conditions inside the transformer produce different gases. So by analyzing what gases are present, you can detect developing problems before they cause failure. This oil testing should happen annually for new transformers, potentially more frequently for older units. It costs a few €100 per test, which seems like an unnecessary expense until you consider that a transformer failure can cost you weeks of downtime and a six-figure replacement cost. The transformer also has various monitoring and protection devices. Temperature sensors, both for the oil and the windings. Pressure relief valves in case of internal faults. Buchholz relays that detect gas formation or oil flow, indicating problems. These protection devices can shut down the transformer before catastrophic failure occurs. Cooling is another consideration. Smaller transformers are often naturally cooled. The oil circulates by convection and dissipates heat through radiators on the transformer casing. Larger transformers might have forced cooling with fans. These fans need to work reliably, especially during high production periods in summer. A failed cooling fan can cause the transformer to overheat and shut down. The substation also includes switchgear, the circuit breakers, disconnectors, and protection relays that control power flow and provide protection. This is medium voltage equipment, which means it's serious engineering requiring qualified personnel to maintain. Medium voltage switchgear maintenance includes contact inspection, insulation testing, mechanical operation testing, and protection relay testing. These relays are what disconnect the system when faults occur, so they need to function correctly. We test them annually, applying test signals to verify they trip at the correct settings. The substation typically has a control building or cabinet. This houses the protection relays, metering equipment, communication systems, and sometimes auxiliary power supplies. It's climate controlled. Electronics don't like temperature extremes or humidity. Maintenance here includes checking HVAC systems, battery backup systems, communication links. From an O&M perspective, the substation is a critical single point of failure. If your transformer fails, your entire farm is down. This is why monitoring is important. Transformer temperature, oil level, cooling system operation, protection system status. Any anomalies need investigation. We've seen transformer failures caused by various issues. Lightning strikes despite surge protection, internal insulation breakdown due to aged oil, external damage from animals. We had one case where a bird built a nest on a transformer bushing, causing a tracking fault. Manufacturing defects that don't manifest until years after installation. Prevention is better than repair with transformers. Good maintenance, proper monitoring, keeping the area around the substation clear of vegetation and debris, ensuring protection systems work correctly. An hour of preventive work is worth weeks of replacement time and hundreds of thousands in costs. Transformer replacement, if necessary, is not trivial. These are large, heavy objects. You need a crane, specialized transport, qualified personnel for installation and commissioning. Lead times can be several months for new transformers, especially for non-standard specifications. This is why having insurance that covers transformer failure is advisable. Section 3. Medium voltage distribution. The AC collection system, 6 to 8 minutes. From the transformer, we work backward to the medium voltage collection system, though in some installations, the topology is different. Let me explain the typical configurations. Smaller solar farms, let's say under 5 megawatts, often have a simple structure. All the inverters connect to a common low-voltage busbar, which feeds directly into one transformer. Simple, effective, fewer components. Larger installations often use a medium-voltage collection system. Multiple transformers, each serving a section of the farm, all connecting to a medium-voltage busbar or ring system, which then connects to the main grid transformer. This is more complex but provides redundancy and reduces losses. In a medium voltage collection system, each inverter or group of inverters has its own step-up transformer. Smaller units, maybe 1 to 2 MVA. These are sometimes integrated into inverter stations. The outputs from these transformers connect via medium voltage cables to the main substation. These MV cables are substantial pieces of kit. We're talking about 3-phase cables, typically XLPE insulated, rated for 10 to 30 kilovolts. They're buried underground, usually in trenches with bedding and warning tape above them, so that future excavation doesn't accidentally dig into live cables. MV cable installation quality matters enormously. Poor installation, inadequate bedding, sharp objects in the trench, insufficient burial depth, inadequate cable supports at terminations, causes problems later. Cable faults are expensive to locate and repair. You need specialized fault location equipment, excavation, splicing, or replacement, and you lose production during the repair. Cable terminations are critical points. This is where the cable connects to equipment, transformers, switchgear, inverters. The termination must be done correctly with appropriate stress control, insulation, and sealing. Poor terminations cause partial discharge, which degrades the insulation over time and eventually causes failure. From an O&M perspective, buried MV cables are mostly worry-free if installed correctly. The problems occur from external damage, excavation accidents, rodent damage in some locations, ground movement, or settlement. We inspect cable routes annually looking for signs of disturbance, ensuring route markers are visible, checking that nothing has been built or planted over cable routes. Partial discharge testing is possible for MV cables and can detect developing insulation problems before they cause failure. This is specialized work requiring expensive equipment, so it's usually done on a periodic basis rather than continuously, perhaps every 5 years or more frequently for older installations. The MV switchgear in larger installations, the ring main units, circuit breakers, disconnectors, requires similar maintenance to the main substation switchgear. Annual inspections, periodic testing, keeping equipment clean and dry. Medium voltage systems also require proper earthing, multiple earth electrodes, earth grids under substations, equipotential bonding. This protects personnel and equipment from fault currents and lightning strikes. Earth resistance testing should be done periodically to ensure the earthing system remains effective. Lightning and surge protection is another aspect. Solar farms are often in open areas, making them vulnerable to lightning. Surge protection devices at strategic points in the MV system protect against lightning-induced voltage spikes. These SPDS have finite lifespans and can fail, either short circuit or open circuit. They should be tested annually. The practical challenge with MV systems is that they require specialist knowledge and qualifications. You can't just send anyone to work on medium voltage equipment. In most European countries, you need specific high voltage authorizations. This means that MV maintenance typically requires bringing in specialized contractors or having specifically qualified personnel on your O&M team. Documentation is particularly important for MV systems. Single-line diagrams showing the electrical configuration, protection settings, cable routes and specifications, earthing system details, test certificates. If something goes wrong, you need to quickly understand the system configuration to diagnose and fix it safely. Right? Let's talk about inverters. These are the devices that convert DC power from your solar panels into AC power for the grid. They're also, from an O&M perspective, the most temperamental components in a solar farm. Inverters are complex power electronics. Inside an inverter cabinet, you have DC input from the panels, filtering and protection circuitry, the actual DC-AC conversion done by IGBT, or similar semiconductor switches operating at high frequency, AC filtering, control electronics, monitoring systems, cooling systems, and communication interfaces. It's sophisticated engineering, and there's a lot that can go wrong. Let's start with sizing and configuration. Inverters are typically sized at 1 to 2 megawatts for utility-scale installations, though ranges from 500 kilowatts to 3 megawatts or more exist. The DC input is usually oversized relative to AC output. You might have 1,400 kilowatts of DC panels connected to a 1,000 kilowatts AC inverter. This is called DC to AC ratio or oversizing, and it's economically beneficial because it maximizes energy production without dramatically increasing costs. String inverters versus central inverters is a design choice made during construction. String inverters are smaller units, maybe 50 to 100 kilowatts, with each one serving a smaller section of the array. Central inverters are larger, 1 megawatt plus, serving large sections. String inverters provide more granularity and redundancy, but more individual components to maintain. Central inverters are fewer units, but larger single points of failure. Both approaches work, both have trade-offs. Modern inverters do more than just DC to AC conversion. They provide maximum power point tracking, constantly adjusting operating voltage to extract maximum power from the panels. They provide grid support functions, reactive power control, voltage regulation, frequency response. They monitor string performance, provide fault detection, and communicate with the SCAMA system. From an O&M perspective, inverters are high-maintenance components. Not constantly, but they require regular attention. Cooling is critical. Inverters generate heat. Several percent of throughput power becomes waste heat. They need to dissipate this heat or they overheat and derate or shut down. Most inverters use forced air cooling with fans. These fans run constantly during operation, which means they wear out. Fan bearings fail, blades accumulate dust, motors burn out. Fan maintenance is important. Clean the fans and air filters regularly. How regularly depends on the environment. A farm in a dusty agricultural area needs more frequent cleaning than one in a clean northern European forest. Dirty fans and filters reduce cooling effectiveness, causing the inverter to run hotter and potentially derate. We schedule inverter filter cleaning quarterly for most installations, monthly in particularly dusty locations. It's simple work. Open the cabinet, vacuum or brush the filters, check the fans visually, close it up. Takes perhaps 20 minutes per inverter. But skip it for a year and you'll have overheating problems. The power electronics inside inverters degrade over time. IGBTs and capacitors have finite lifespans. Electrolytic capacitors in particular are temperature sensitive. Running hot accelerates their aging. This is why keeping inverters cool matters not just for immediate performance, but for long-term reliability. Inverter failures are common, not catastrophically common. A well-maintained inverter might run for 5 to 10 years before major component replacement is needed. But problems do occur. Control board failures, IGBT failures, capacitor aging, sensor failures, communication issues, software glitches. When an inverter fails, your response time matters enormously. A 1 megawatt inverter producing at 800 kilowatts in summer generates perhaps 5,000 euros of revenue per week. If it's down for 2 weeks, that's 10,000 euros lost. If it's down for 2 months due to parts availability or contractor scheduling, that's 40,000 euros or more. This is why spare parts matter for inverters. At minimum, you should have spare control boards, spare fuses, spare fans. Ideally, complete spare inverters or service exchange agreements with the manufacturer. When something fails, you want to be able to fix it immediately, not wait weeks for parts. Inverter manufacturers provide varying levels of support. Premium brands typically have better service networks, faster parts availability, and more responsive technical support. Cheaper brands might save money on initial capital expenditure but cost more in downtime when problems occur. Firmware updates are another consideration. Manufacturers periodically release firmware updates that fix bugs, add features, or update grid code compliance. These updates should be tested and deployed in a controlled manner. We've seen firmware updates that caused more problems than they solved, so we're conservative about updating production systems. Inverter monitoring integration is critical. The inverter should be reporting status, production, alarms, and detailed operating parameters to your SCADA system. If monitoring isn't working, you don't know what the inverter is doing, which means problems go undetected. We've taken over farms where inverter monitoring was partially broken. Maybe 60% of inverters were reporting properly, 40% were not. The previous O&M provider hadn't bothered to fix it. This is unacceptable. If you can't monitor it, you can't maintain it properly. Inverter location and access matters for O&M. Inverters in weather-protected buildings are easier to maintain than outdoor inverters. Inverters with good access roads can be reached in all weather. Inverters in the middle of muddy fields become difficult to service in winter. These seem like minor considerations during design, but they matter when you're trying to fix something in January. The practical reality with inverters: they're complex electronics operating in challenging environments. They need regular maintenance, cleaning, inspections, monitoring. They will fail occasionally and need repair. Having good spare parts availability, qualified technicians, and responsive support makes all the difference between minor issues and expensive downtime. Now we're getting closer to the actual solar panels. Between the panels and the inverters, there's the entire DC system, the strings, DC cabling, combiner boxes, and all the associated protection and monitoring equipment. Let's start with string configuration. A string is a series connection of solar panels, typically 15 to 30 panels connected positive to negative. Connecting them in series adds up their voltages. If each panel is 40 volts, 30 panels gives you 1,200 volts DC. This high voltage reduces current for the same power, which reduces resistive losses in the DC cabling. String length is a design compromise. Longer strings mean higher voltage and lower current, which is good for efficiency. But longer strings also mean that shade or failure of any panel affects the entire string's performance. Shorter strings provide more granularity but more parallel connections, and potentially more cable. Multiple strings connect in parallel to feed an inverter. This parallel connection typically happens in combiner boxes, essentially junction boxes where multiple string cables come together into a single DC output to the inverter. DC cabling needs to be properly specified. We're talking about 1000 to 1500 volts DC in most modern systems. The cables must be rated for this voltage, UV resistant if exposed to sunlight, resistant to temperature variations, and mechanically robust. Undersized or poor quality DC cables cause resistive losses and potential fire hazards. DC connectors are critical points. These are the plug-and-socket connections between panels, between strings and combiner boxes, between combiner boxes and inverters. They must be properly rated, correctly assembled, and weather-sealed. Poor DC connections are a common source of problems. A connector that's not fully clicked together, or has corroded contacts, or is damaged by UV exposure creates high resistance. This causes power loss and heat generation. In extreme cases, it can cause arcing and fire. We do thermal imaging surveys specifically to find bad DC connections. They show up as hotspots in the thermal camera. Finding and fixing them is straightforward once identified, but if they're not caught, they cause ongoing losses and potentially catastrophic failure. Combiner boxes serve multiple functions. They're the physical junction point for string cables. They typically contain fusing for each string. If a string develops a fault, the fuse protects it. They might contain string-level monitoring, measuring current and voltage for each string individually. They provide a test and disconnection point. From an O&M perspective, combiner boxes need periodic inspection. Check for water ingress. The seals can fail, and water in a combiner box causes corrosion and tracking. Check for signs of overheating at connections. Test the fuses, verify the monitoring is working correctly. Combiner box placement during design matters for maintenance access. Boxes placed in locations that become inaccessible due to vegetation, flooding, or just inconvenient distance from access roads make maintenance harder. Good design considers not just the electrical requirements, but also the practicalities of someone needing to access that box in various weather conditions throughout the year. String-level monitoring is increasingly common. Each string has a monitoring device that reports current, voltage, and sometimes more detailed parameters. This gives you granular visibility. You can see if individual strings are underperforming. The value of string monitoring depends partly on how you use the data. If you're just collecting it but not analyzing it, it's not particularly useful. But if you're actively monitoring for underperforming strings and investigating the causes, it helps identify problems early. Shading, soiling, module faults, connection issues. DC surge protection is another component in the DC system. SPDS protect against lightning-induced surges. They're typically installed at combiner boxes and inverter inputs. Like all SPDS, they can fail and should be tested periodically. Earthing and bonding in the DC system is important for safety. The panel frames are bonded together and connected to earth. This ensures that in case of insulation failure, fault current can flow to earth and trip protection devices rather than leaving metalwork at dangerous potential. The practical challenges with DC systems are that they're distributed across the entire array, often in relatively hostile outdoor environments. Connections are exposed to UV, temperature cycling, moisture. Cables can be damaged by animals, inadvertent vehicle traffic during maintenance, or just UV degradation over decades. Periodic inspection, visual inspection of cables and connections, thermal imaging, testing of protection devices, is essential. The DC system is where faults often develop gradually. A connection that's slightly degraded might cause 1% power loss initially. Over months or years, the degradation worsens, losses increase, and eventually it fails completely. Catching it early through monitoring and inspection is much more economical than waiting for failure. Right, we've finally reached the actual solar panels. After all the infrastructure and power electronics, we arrive at the devices that actually generate the electricity. Solar panels, photovoltaic modules, are remarkably simple devices externally. A layer of solar cells, typically 60 or 72 cells for traditional modules, though half-cut and other configurations exist. The cells are encapsulated in EVA, ethylene vinyl acetate, with a glass front sheet and either glass or polymer back sheet, all held in an aluminum frame. Junction box on the back with bypass diodes and output cables. Electrically, modern modules are rated around 400 to 600 watts peak power, with higher wattages becoming increasingly common as cell efficiency improves. Voltage is typically 30 to 50 volts at maximum power point. These specifications determine how you configure strings and size your DC system. From a maintenance perspective, panels themselves are quite low maintenance. They're solid-state devices with no moving parts, designed to survive outdoors for 25 years. But low maintenance doesn't mean no maintenance, and various things can go wrong. Physical damage is the most obvious issue. Hail, falling branches, vandalism, installation accidents. Cracked glass or damaged cells reduce output. Severe damage requires module replacement. Minor cracks might not require immediate replacement but should be monitored, because they can worsen over time. Hotspots are a thermal phenomenon where part of a module runs significantly hotter than the rest. This typically indicates a problem: cell cracking, solder bond failure, shading causing reverse bias, bypass diode failure. Hotspots are detectable through thermal imaging and should be investigated. Persistent severe hotspots can lead to permanent module degradation or even fire risk. Potential induced degradation, PID, is a phenomenon where leakage currents between cells and the frame cause performance degradation. It's more common in certain environmental conditions and module types. Proper system grounding and module selection can mitigate PID. Testing for PID requires specialized equipment, but is worthwhile if you suspect it's occurring. Delamination is when the encapsulation layers separate, usually visible as bubbles or white patches in the module. It indicates manufacturing defects or moisture ingress. Delaminated modules should be replaced under warranty if still covered. The junction box on the back of each module contains bypass diodes. These allow current to bypass a shaded or failed cell, so it doesn't drag down the entire string. Diode failure is relatively common, perhaps 1 to 2% over the module lifetime. A failed bypass diode doesn't stop the module working, but reduces its effectiveness when partial shading occurs. Panel degradation is normal. Modules lose efficiency over time, typically 0.5% per year. This is expected and factored into financial models. The manufacturer's performance warranty guarantees minimum output after 25 years, usually 80 to 82% of original rating. If modules degrade faster than warranted, that's a warranty claim. Testing module performance in the field is challenging. You can measure voltage and current, but determining actual power output relative to rated capacity requires knowing the exact irradiation and temperature conditions, which requires calibrated reference cells. Professional four-curve testing equipment can characterize module performance, but it's specialized and time-consuming. In practice, we rely mostly on string-level performance monitoring. If a string is consistently underperforming compared to adjacent strings in similar conditions, that indicates a problem requiring investigation. Now, mounting structures. These are the frameworks that hold the panels, the racking systems. They're typically aluminum or galvanized steel, designed to support the panel weight and withstand wind loads. Mounting structures are surprisingly maintenance-intensive, not because they fail often, but because there are so many individual components. Thousands of clamps, bolts, grounding connections, foundation posts. Each one needs to be installed correctly and remain secure over decades. Corrosion is the primary enemy of mounting structures. Despite galvanization or aluminum's natural oxide layer, corrosion does occur, particularly in coastal environments with salt exposure or in industrial areas with atmospheric pollution. Annual visual inspections should check for corrosion, with particular attention to dissimilar metal junctions where galvanic corrosion can occur. Structural integrity checks are important. Are the structures still level and aligned? Any signs of foundation movement or settlement? Any loose bolts or damaged clamps? Wind vibration over years can loosen fastenings, requiring periodic torque checks. Grounding connections between panels and structures need to maintain electrical continuity. These can corrode or work loose. Testing grounding continuity should be part of periodic inspections. Fixed tilt versus tracking systems is a major distinction. Fixed tilt structures are simpler, just frameworks holding panels at a fixed angle. Trackers have motors and controls that adjust the panel angle throughout the day to follow the sun. Trackers increase energy yield by 15 to 25%, but add mechanical complexity and maintenance requirements. Tracker maintenance includes lubrication of moving parts, motor and gearbox inspection, controller calibration, checking for mechanical binding or damage. Tracker systems can fail in various ways. Motors burn out, sensors fail, controllers malfunction, mechanical jamming occurs. When trackers fail, you typically revert to a safe position rather than leaving panels in potentially wind-vulnerable orientations. The practical reality with panels and structures, they're the visible part of the solar farm, spread across potentially several hectares. Maintenance requires physical access to all areas, ability to work at height in some configurations, and systematic inspection procedures. Individual component failures are common, simply due to quantity. If you have 30,000 panels and mounting clamps, even a 0.1% failure rate means 30 failures needing attention. We've discussed the power generating equipment. Now let's talk about the monitoring and control systems, the nervous system of the solar farm that tells you what's happening and allows you to control operations. At the heart of this is the SCADA system, supervisory control and data acquisition. This is software, usually running on an industrial PC in the substation control room, that collects data from all the monitored equipment, stores it, displays it, analyzes it, and generates alarms when problems occur. The SCADA system communicates with various devices throughout the farm. Inverters reporting their status and production, weather stations providing irradiation, temperature, wind, and sometimes precipitation data, string monitors or combiner box monitors reporting DC side performance, the transformer and substation equipment reporting status, potentially meters, security systems, environmental sensors. All this data arrives at the SCADA system, typically via communication networks using protocols like Modbus, IEC 61850, or proprietary manufacturer protocols. The data needs to be collected reliably, which means the communication infrastructure needs to work reliably. Communication networks in solar farms are often a mix of wired and wireless. Hardwired Ethernet or serial connections for equipment in buildings. Fiber optic for longer distances or where high reliability is needed. Wireless radio links for equipment spread across the site. Sometimes cellular modems for remote access. These communication systems fail. Cables get damaged. Wireless links are affected by interference or obstacles. Network switches fail. Configuration gets corrupted. When monitoring fails, you lose visibility. You don't know what the farm is doing, which means problems go undetected. We prioritize communication system maintenance specifically because it's so critical for everything else. Check all communication links quarterly. Test backup communication paths if they exist. Ensure remote access works so you can monitor the farm from offsite. The SCADA software itself requires maintenance. Operating system updates, security patches, software updates from the SCADA vendor, backup procedures. Industrial control systems are increasingly targets for cyber attacks, so cybersecurity is becoming an important consideration. Proper network security, firewalls, access controls, regular security audits. Data analysis is where SCADA systems provide value beyond just display. Calculating performance ratios, availability metrics, loss analysis. Comparing actual production to expected production based on weather models. Identifying underperforming equipment or sections of the array. Generating reports for asset managers and investors. The quality of this analysis depends on proper configuration. The SCADA system needs accurate models of expected performance. It needs properly configured alarm thresholds. It needs proper data validation to reject bad sensor readings. We've seen SCADA systems that were technically collecting data but not doing useful analysis, which means they weren't really fulfilling their function. Alarm management is critical. The SCADA should alert operators to problems that need attention. But if it generates too many false alarms, operators start ignoring them, the crying wolf problem. If it generates too few alarms, problems aren't detected promptly. Good alarm management means setting appropriate thresholds, filtering out transient issues that self-resolve, prioritizing alarms by severity, and ensuring someone actually responds to alarms promptly. We use a tiered alarm system, critical, major, minor, with different response time requirements for each tier. Remote monitoring is standard practice. You shouldn't need someone physically on site to know what's happening. The SCADA system should be accessible remotely, typically via secure VPN, so operators can monitor performance, diagnose problems, and sometimes even control equipment remotely. However, remote monitoring has limits. You can see data and trends, but you can't see physical conditions. Is there unusual vegetation growth? Is equipment visibly damaged? Is there flooding or access issues? This is why remote monitoring complements but doesn't replace site visits. Weather monitoring deserves specific mention. Accurate irradiation measurement is essential for performance analysis. If your irradiance sensor is reading incorrectly, maybe it's dirty or miscalibrated, your performance calculations will be wrong. You might think the farm is underperforming when actually the sensor is giving bad data. We calibrate irradiance sensors annually against reference standards. We clean them regularly. We compare readings from multiple sensors if available to detect anomalies. This sounds pedantic, but irradiance data is fundamental to everything else. The practical point about monitoring systems: they're infrastructure that enables everything else. Without reliable monitoring, you're operating blind. With good monitoring, you catch problems early, optimize operations, and demonstrate performance to stakeholders. It's worth investing in proper monitoring infrastructure and maintaining it diligently. Right? We've covered all the electrical systems. Now let's discuss the supporting infrastructure. The unglamorous stuff that doesn't generate electricity but is necessary for the farm to function. Access roads are more important than they might seem. A solar farm needs internal roads for several reasons: construction access initially, ongoing maintenance access, emergency access, security patrols. These roads need to be passable year-round, including in wet conditions. Road quality varies enormously across sites. Some farms have proper stone or gravel roads that remain passable in all weather. Others have minimal roads that turn to mud in winter. The quality of your access roads directly affects maintenance efficiency. If your technicians can't reach a failed inverter because the road is impassable, your repair time extends from hours to days, waiting for conditions to improve. Road maintenance is ongoing. Gravel needs periodic replenishment. Drainage needs to be maintained so water doesn't wash out the road base. Vegetation encroaching on roads needs to be controlled. In northern climates, snow clearing might be necessary. We factor road quality into our O&M planning. Sites with poor roads require more time allowance for maintenance activities, particularly in winter. Sometimes road improvement is necessary. Spending money on better roads saves money on maintenance access delays. Drainage across the site is another infrastructure consideration. Solar farms are large flat or gently sloped areas. Water needs somewhere to go. Poor drainage causes flooding, which can damage equipment, make access difficult, and cause erosion. Drainage might include perimeter ditches, culverts, swales, or deliberate grading. This infrastructure needs periodic inspection and maintenance. Ditches fill with vegetation and sediment. Culverts block. Erosion creates gullies that damage cables or undermine structures. Fencing is almost universal for utility-scale solar farms. This serves security purposes, preventing theft and vandalism, and safety purposes, keeping unauthorized people away from energized equipment. Typical fencing is 2-meter chain link with barbed wire on top, gates at access points with locks. The perimeter can be several kilometers for large installations, which is substantial infrastructure requiring maintenance. Fencing degrades over time. Posts corrode or shift. Wire rusts. Animals dig under fences. Vegetation grows through fencing. Annual inspections should check fence integrity and repair damage. Security systems go beyond just fencing. Many farms have perimeter intrusion detection, sensors that detect fence climbing or cutting, CCTV cameras covering key areas, the substation, inverters, gates, motion-activated lighting, alarm systems connected to security monitoring centers. These security systems require maintenance. Cameras fail or get obscured by vegetation or dirt. Sensors need battery replacement. Communication links for alarm transmission need testing. We've seen security systems that were nominally present but non-functional because they weren't maintained. The security threat varies by location. Some regions have significant theft risk. Copper cabling is valuable, electronic components are valuable, even the panels themselves can be stolen. Other locations have minimal theft risk but vandalism concerns. Security infrastructure should be appropriate to the actual risk level. Lighting is necessary around the substation and potentially at inverter stations for maintenance work and security. This is typically LED lights powered from the farm's auxiliary power system. Lights fail occasionally and need replacement. Photocells or timers controlling lighting need to function correctly. Auxiliary power infrastructure, the 230-volt alternating current supply for the site facilities, control systems, lighting, security, typically comes from the grid via a separate connection or from the farm's own production. This needs to be reliable because if auxiliary power fails, you can lose monitoring, control, and security systems. Site buildings vary by installation. Minimum is usually a substation building or control room, housing the SCADA system, protection equipment, spare parts, and work facilities. Larger sites might have maintenance buildings, warehouses, office facilities. These buildings require basic maintenance. Roofs, HVAC systems, doors and locks, shelving, and equipment storage. It sounds mundane, but a leaking roof that damages your SCADA server or spare parts inventory is a genuine problem. Signage and markings are another detail. Warning signs for electrical hazards, safety instructions, equipment identification labels, cable route markings. Over time, signs fade or fall off. Cable markers get buried or lost. Maintaining proper signage matters for both safety and operational efficiency. Environmental management might include measures like wildlife-friendly fencing, habitat creation, pollution prevention. Some farms have environmental monitoring requirements as conditions of planning permission. This is operational responsibility requiring periodic documentation. The key point about support infrastructure, it's not glamorous. It doesn't generate revenue directly, but it enables everything else. Good access roads make maintenance efficient. Good security prevents losses. Good drainage prevents damage. These unglamorous systems deserve attention in any professional O&M program. So we've walked through a solar farm from grid connection to perimeter fence, looking at every major system and component. Quite a lot of infrastructure for something that's just panels sitting in a field, isn't it? The important point is that all these systems are interconnected. A problem in one area affects others. Poor vegetation management causes shading, reducing panel output. Failed cooling fans cause inverter derating. Damaged access roads delay maintenance responses. Inadequate monitoring prevents problem detection. Corroded DC connections cause losses that compound over years. This is why professional O&M takes a systematic approach. You can't just focus on one area, the panels or the inverters, and ignore everything else. The entire system needs attention. Each component has its maintenance requirements, failure modes, and impact on overall performance. When we take over O&M contracts, one of the first things we do is a comprehensive site assessment. Walk the entire facility, inspect every system, review all documentation, test all monitoring. Often we find issues the previous O&M provider missed or ignored. These issues are usually straightforward to address once identified, but they were causing ongoing performance degradation. Understanding solar farm anatomy from a maintenance perspective means knowing not just what components exist, but what their failure modes are, how to detect problems, what the economic impact of various failures is, and how to prioritize maintenance activities for best overall results. It means knowing that the transformer oil should be tested annually, that inverter filters need quarterly cleaning in dusty environments, that DC connections should be thermally scanned annually, that access roads need gravel replenishment every few years, that security cameras need periodic cleaning, that the SCADA system backup should be tested monthly. All of these details matter. Individually, each one is small. Collectively, they're the difference between a solar farm that performs at 95% of expected output for 25 years and one that degrades to 80% output after a decade. In future episodes, we'll dig deeper into specific systems and maintenance activities. We'll talk about advanced diagnostics. We'll discuss failure modes in detail. We'll explore maintenance strategies and optimization. But for today, the message is this. A solar farm is a complex system with many interconnected components. Understanding that system, not just theoretically but practically, from the perspective of someone who has to maintain it, is essential for effective O&M. If you're investing in solar farms, make sure you understand what you're investing in. It's not just panels, it's an integrated electrical generation facility with multiple voltage levels, power electronics, monitoring systems, and substantial support infrastructure. If you're developing solar farms, design with maintenance in mind. Component selection, access arrangements, monitoring infrastructure, documentation. These decisions during development affect O&M costs and performance for decades. If you're operating solar farms, approach it systematically. Every component needs attention. Every system has requirements. Professional O&M is comprehensive, not selective. This is Lighthief reminding you that solar farms are simultaneously simpler and more complex than they appear. Simple in principle, panels convert light to electricity. Complex in execution, dozens of systems and thousands of components, all needing to work together reliably for 25 years. Next time, we'll be exploring specific maintenance activities and diagnostic techniques in more detail. Until then, may your transformers stay cool, your inverters stay online, and your access roads stay passable.